Welcome to the massive open online course on Aspen Plus. In today's lecture, we are going to discuss about the fabric filter, or in Aspen it is called FabFL block. FabFL is a gas-solid separation model which is used to separate inlet gas stream containing solids into a solid stream and a gas stream carrying the residual solids. Various types of gas-solid filters are available, and they are largely grouped into two major groups. One is surface filter type, another is depth filter type. That means whether the filtration is happening at the surface or the filtration is happening in depth. And the filters may also be divided into groups based on the filter material, whether the filter material is fabric or it is some granules. Today we are going to discuss about the bag filter, which is a fabric type of filter and it's a surface filter. That means the bag is made of a fabric and the filtration happens on the surface of the bag. This is a schematic diagram of a fabric filter, and this structure is called a bag house. And inside the bag house, we will find few long bags. These are bags, perforated bags, and they will be hanging like this. So this is one bag, this is another bag, this is another bag. And these bags are collectively taken inside a cell. And a bag house contains multiple of such cells. The raw gas, which contains the suspended solid materials, they enter through this particular feed line and they get distributed over this region and they go upwards in this fashion, and the gaseous component infiltrate through the perforations and reach on the other side of the bag material. Whereas the dust particles, they get arrested on the surface of it and eventually they form a cake on the surface of the bag material or on the fabric of the bag material. So just like a hydrocyclone separator, or for that matter any solid liquid filter, here also there are two types of resistance. One resistance is due to the filter medium and the other resistance is due to the filtration cake formation. So the clean gas escapes through this exit, whereas the solid particles which got arrested on the surface, they form a cake and eventually they are separated through this dust collector. That's how the fabric filter works. Just like a previous few models that we have learned, the fabric filter also can be run in two modes. One is simulation mode, another is design mode. That means simulation mode will do the rating calculation, whereas design mode will calculate the sizing calculation. So in the simulation mode, you have to specify the filtration area or the bag house characteristics. The bag house characteristic means you have to provide the total surface area of the fabric material of the bag. You have to specify the number of such bag in a cell and number of such cells. So if you multiply all those three, then you will get the total filtration area. Or you can specify the total filtration area directly. And then the FabFL calculates the filtration velocity. And in the sizing calculation, in the design mode, you have to specify the filtration velocity and it will calculate the filtration area, or if you want, it can calculate the bag characteristics as well. And in the sizing or rating calculation, you have to specify the maximum allowable pressure drop or the average pressure drop, and it will calculate the filtration time. And if you specify the filtration time, then it will calculate the pressure drop. So either of them you have to enter, and FabFL calculates the other one successively. So these are the operating ranges of the FabFL model, because if you calculate something outside the FabFL model, then the results may be unrealistic. So what are the operating ranges? The diameter of the solid particles should lie between 0.1 to 100 microns. Okay. So FabFL model will give best result if your solid particles lie between 0.1 to 100 micron size. And the maximum velocity through the cloth, it should fall between 20 to 40 foot per minute. So maximum pressure drop should not go beyond that. And the calculation of gas velocity is very easy. It is the total gas volumetric flow rate by the total filtering area. Now let us go to the Aspen Plus simulation window and see what are the other parameters that we have to specify. So this is the Aspen Plus simulation window, and you will get the solid separator over here. So this is the gas solid separation using fabric filter. So you can bring it over here. So this is a feed, this is gas, and this is solid. So it is gas solid separator. Now let us rename them. Let us give a name of feed. This is gas and this is solid. Okay. Now go to the block B1 fab filter. Okay. Now let us see what are the types of models we have. As expected, we have a solid separator model, which we already know, nothing new about it. And the second model is fabric filter. So practically there is only one model over here, fabric filter model, and two modes of run. One is simulation and another is design. We know what they are, we have already discussed. The filtration velocity calculation, it is on the basis of total area or the baghouse characteristics. As I said, that you can give the total filtration area or you can give the baghouse characteristics. So if you choose the baghouse characteristics, then you have to provide this information. You have to provide the number of cells and you have to provide the number of clean cells. That means those cells you have to subtract from the number of cells because there's a cleaning cell. So number of bags per cell you have to provide, then filtering area per bag, that also you have to provide, and you have to provide the time required to clean a bag. So this information that you have to provide, some default values are given over here, but when you want to run the operation, then you have to give the correct values as per your requirement. So this is about the baghouse characteristics. Now, if you choose the calculate from total area, then the baghouse characteristics will be inactive, whereas the total filtering area is active. Okay, so you have to provide this total filtering area. Baghouse characteristics is not required. Okay, so these are the two cases you have. So by default, total filtering area will be inactive, baghouse characteristics will be active. Now, pressure drop or filtration time can be calculated based on various calculation method. The first one is filtration velocity function. And the filtration velocity function will be of this nature. This is the function. Delta P is equal to A plus B into V plus C into V squared. So this is a small polynomial equation. And this polynomial equation, or second degree polynomial rather, so you can provide the velocity unit in terms of whichever unit that you choose, and the pressure and the constant A, B and C you have to provide based on the velocity unit and pressure unit you choose. So this particular function you have to provide. So here it is given in detail. In the polynomial method, coefficients A, B and C must be specified, where V gas is the gas velocity through the cloth. Okay, so this is the equation, and for more information you have to go to the filtering time. Now you see the filtering time. Now as I said, either you have to provide the velocity or the time. If you provide the information about the pressure drop, then filtration time will be calculated, and if you provide the filtration time, then pressure drop will be calculated. So go to filtering time. So FabFL calculates the filtering time in this fashion. So you have given the pressure drop information over here. So delta PF is the final pressure drop across the collected dust and filter cloth, whereas the pressure drop of the clean bag, because filtration medium also will have some resistance to the flow of gas. So even the clean bag will have some pressure drop. So that is the minimum pressure drop. Even if you do not have any dust material that has covered the filter surface, even then there will be some minimum pressure drop due to the clean bag. So final pressure drop across the collected dust and filter cloth, that means when the filter cloth is covered by the dust, so that is the final pressure drop minus the initial pressure drop, that by the dust concentration, dust resistance coefficient, and the V0 square, that is air to cloth ratio, that is the gas velocity through the cloth, the ratio of gas volumetric flow rate by the total filtration area, which can be calculated by this small equation, where Q is the volumetric flow rate of the gas, and here you have number of cells minus the number of cells being cleaned, because the number of cells which are being cleaned cannot be used for the filtration because that is being cleaned. So number of cells minus the number of shells being cleaned multiplied by the number of bags per cell multiplied by the total filter surface of bag. Okay, so if you multiply all of them, then you will get the total filtration area, and if you divide Q by the total filtration area, you will get the air to cloth ratio V0, that is the gas velocity through the cloth. This air to cloth ratio can also be determined from the basic air to cloth ratio in this fashion. So basic air to cloth ratio is this. So for activated carbon, the basic air to cloth ratio is minimum 2.5, maximum 2.8, average 2.65. For aerosol, you have some other set of data. Alfalfa meal intake hopper, alkali cellulose, almonds, alum, alum earth. So for various types of material, we have the sets of information about V mean, V max and V average. So these are the basic air to cloth ratio for various types of filters. Now once you know this basic air to cloth ratio, you can multiply this basic air to cloth ratio and various factors like factors A to H. So VB into A into B into C, D, E, F, G, H. So what are these A, B, C, D, E, H? they are found over here. So the factor A depends on the filtering and regeneration system. For instance, if the filter is a shaker and reverse air filter pockets, the shaker means there is a shaker mechanism whereby the bag or the arrangement which holds the bag that shakes. And as a result, the dust particle attached with that fabric, they fall down due to the shaking and they are arrested in the dust collector. So that is one way of cleaning the fabric material. Okay, and there might be a reverse air filter. That means the air might be flown in the reverse direction of the filtration medium so that the particles which are covering the surface of the filter media, they get detached and they fall. So how the filter and regeneration system is, based on that, the factor A can be decided. So if that type of filter and regeneration system is there, then we can take A is equal to 0.45. Similarly, if it is a jet filter with venturi in pocket arrangement, then it is 0.5. If direct pulse filter, then it is 1.5, etc. Then factor B, there are various applications of them. Extraction at material transfer points or conveyors or packing or sieves. For that, factor B is 1. For exhaust gases from furnace, dryers and reactors, then it is 0.8 and so on. So this is factor B. Like that, there are several factors A, B, C, D. D will be calculated based on the dust load. If C is the dust concentration, that is the mass of solid by volume of gas flow, then D can be calculated by this equation. Similarly, the factor E can be calculated, factor F can be calculated, G, H, everything will be calculated. And then all the factors multiplied by the basic air to cloth ratio, which we have already discussed right now. So that can be taken as the final V0. So with that, the filtering time can be calculated. And in case you provide the filtering time, then the pressure drop can be calculated directly over here. This is the pressure drop of the filter kit. Delta PS is Ks multiplied by eta into HT into V. H is dependent upon time, where D is the filtering time. Ks is the filter cake resistance. Eta is dynamic gas velocity. H is the height of filter cake, because as the time progresses, the height will also increase. The height means the thickness of the filter cake. C is dust loading. E is the total degree of separation. T time, density of solids, and porosity of filter cake are also given over here. So based on them, you can find out the pressure drop. I mean, these are either available in the property database or you have to provide this data. So from there, the Aspen Plus will calculate the pressure drop. And combining this equation, you can find the maximum time interval between the cleanings, that is T clean. It can be calculated over here. So delta P max is the maximum allowed pressure drop. And the maximum height or the thickness of filter cake also can be calculated from this equation. So you need to provide this information over here. So this is by filtration velocity function. Here you have to provide the outlet solids stream pressure. Now outlet solid stream pressure, it can calculate from the pressure drop, or you can copy it from the inlet pressure. That means inlet pressure and outlet pressure is same. Or you can use the ambient pressure. It will be ambient to the device, mostly 1 atmosphere. Or you can specify the pressure. If you choose specify the pressure, then you have to specify it over here. Otherwise, it will be inactive. If you choose something else, suppose if you choose this one, it will be inactive. If you choose it here, it will be inactive. If you choose use ambient pressure, it will be inactive. But the moment you choose specify pressure, then it will be active and you have to specify the pressure. And then the pressure drop can also be calculated from the specific resistance. As I already told you, the resistances are two types over here. One is due to the filter medium, that is the inherent resistance due to the fabric, and also the filter cake resistance. That means as the filtration progresses, the layers of dust will be created on the surface of the fabric. So resistance due to that. Now you have to specify over here either the maximum pressure drop or you have to specify the filtration time. If you provide the filtration time, maximum pressure drop will be calculated. And then either you have to provide the filter media resistance or you have to provide the pressure drop due to the filter media. You can give the filter media resistance and the pressure drop due to the filter media will be calculated by that information. And then this is the cake resistance. The cake resistance, you can directly provide the information on the dust resistance coefficient. The dust resistance coefficient can be obtained from here. You can see the dust resistant coefficient. If the dust particle diameter is less than 20 micron, then the resistance coefficient will be 300,000. If it is between 20 to 90, it will be 60,000. If it is greater than 90, it should be 15,000. So based on that, dust resistance coefficient can be specified over here. Or you can provide the information on filter cake resistance. So filter cake resistance, you can provide the porosity of the filter cake can be provided. That means either of them you have to provide over here. Okay. And finally, the pressure drop can be constant. That means instead of mentioning the maximum pressure drop or minimum pressure drop, you can directly provide the information on average pressure drop. Okay, so you can specify the average pressure drop, then all sort of calculations are not required. You are just directly giving the information. Next comes the filter operation condition, the filtration velocity. As I have already told you, the operating range, the maximum gas velocity between 0.1 to 0.2. So the maximum velocity should not go beyond 0.1 to 0.2. Here by default they have given 0.02, but you can choose any other value also, but it should not go beyond 0.1 to 0.2. Otherwise the result will be unreliable. That you have to keep in mind. Then comes the efficiency. Now the efficiency also, various models are available. We will look into them one by one. So this is the separation efficiency. Overall, the separation efficiency is defined as the flow rate of the solids removed from the inlet divided by the total inlet flow rate of the solid. Now the separation efficiency is a function of particle diameter of the solid, and you can choose from several kinds of efficiency curve. First one is piecewise linear. Okay, so one is the piecewise linear, and piecewise linear means for the large particle that is greater than 10 micron in average diameter of TPV, the fractional efficiency is 1. So these are for large particle, the efficiency is 1. When the particle is between 1 to 10 micron, then you have to use this particular equation, and when this is less than 1, then you have to use this particular equation. Now this equation, obviously it will be used by Aspen Plus itself. You have to just specify that it is piecewise linear. It will do its own calculation. Next is ideal. Ideal means the separation efficiency is 1 for all sizes. Okay, so that is 100% efficiency. Not a single piece of solid will go to the other side of the filter medium. Okay, so that is the ideal separation. And then exponential separation. Exponential separation, if you choose this one, define with function. So this is the exponential separation curve. This function, it has this V-shaped curve. Okay, so this is the particle diameter and this is the separation efficiency from 0 to 1. Now, for various values of A, B and C, you will get various kinds of this particular curve. Okay. Now, if you choose either of the first two, then A, B and C accordingly are fixed. You do not have to provide them separately. That means if you choose the first one, then A, B and C are automatically chosen for you. A will be 0.065, B will be 16,200 and C will be 0.2. Similarly, if you choose the 95% at 500 nanometer, then it is A is equal to 0.815, B is equal to 272,000, C is equal to 0.16. That means if you choose either of them, they mean the minimum separation efficiency is 90% or 95%, the case you choose, and occurs for particles 500 nanometer in diameter. So minimum separation efficiency is this. Now, in case you are not happy with this 90 or 95%, then you can define your own function with A, B and C. You have to provide this data A, B and C, and then accordingly the separation efficiency will be calculated and that will be used in the function. Okay, so these are the types of efficiency curve that you will get. And the last one is tabulated data. So in case you have the raw data of this, suppose you have done some experiment and if you have got some other kind of curve over there and you have those data, so these data points, you can make a tabular representation of data and then any value within two data can be interpolated either linearly or spline linear or spline RRSB, or it will be done by best fitting. So these things are all well known to you, so you can use the tabular data in this fashion. So these are various efficiency model. And finally, if you convert into design mode, then your filtration velocity information is required and it will calculate the total filtering area. Based on that, the number of cells will be calculated, because number of clean cell, number of bags per cell, those information you have to provide, and it will tell you how many such cells will be required for your bag house. So those are the information will be designed. Okay. Now let us go to an example problem and solve it. That will help us in learning it better.